In this video, we'll be going through question 13 from the 2021 HSC Mathematics Extension 1 exam, and this will be the fourth in a series of 5 videos covering the entire paper. So part A says, a 2-meter high sculpture is to be made out of concrete. The sculpture is formed by rotating the region between y equals x squared plus 1, and y equals 2 around the y-axis. Find the volume of concrete needed to make the sculpture. So we've been given this nice diagram which shows that there's like sort of a bowl shape, and from that bowl shape we've cut out a smaller bowl shape, and what's left over is the volume that we're trying to calculate. And we know that we have the functions y equals x squared and y equals x squared plus 1 involved in the forming of this shape. But I think it'd be good if we'd be able to visualize this by adding in some axes so that we can actually see the graphs and maybe visualize them being rotated about the y-axis. So if we add in a set of axes here, we can see that this outer edge, I suppose, if you like, this is the y equals x squared curve, and then this inner edge, or inner surface, that's y equals x squared plus 1. So we can see that this has been shifted up to 1, or this point here is 1. And we know that it has a height of 2 because we're told that, and that also makes sense because we're told it's the area between the curve y equals x squared and y equals x squared plus 1 and y equals 2. Okay, so in order to work out this volume, you can see that you probably need to calculate the larger shape, the larger bowl, and subtract from that the smaller bowl. And so that's exactly what we're going to do. Our volume is going to be really calculating 2 volumes and then taking the difference. So the larger one, V1, is what we get when we rotate this part of the function, y equals x squared, rotate that around the y-axis, so we're going around like this. And so working out this volume is pi times the integral of, we're going around the y-axis, so it should be x squared dy. And here you can see we're going from 0 to 1, minus pi times the integral of this smaller one now, this smaller region, or I suppose the smaller volume, but that comes from this function, which is y equals x squared plus 1. But once again, we're going around the y-axis, so it should be x squared dy here. I suppose I really should label this as x1 and x2 because they're different x's. But in this scenario, we're only going from 1 to 2. Okay, so we've got, for our first one, the equation of this curve was y equals x squared. And so getting x squared by itself, it's just y. So we're integrating, I should have said not up to 1, that should be going up to 2. So I'm integrating y dy. And here, our curve was, let's do it in orange. This curve is y equals x squared plus 1. And so to make x squared the subject, you just move the 1 over. And so I'm integrating from 1 to 2, I'm integrating y minus 1. And so now it's a matter of integrating, substituting in correctly, and getting our answer. So it'll be pi times y squared on 2, evaluated from 0 to 2, minus pi times y squared on 2 minus y, evaluated from 1 to 2. Subbing everything in, we'll get 2 minus 0. When we sub 2 into this, we'll get 0. And when I sub 1 into that, I get a half minus 1, which is negative a half. So I end up with 2 pi minus a half pi, which is 3 pi on 2. And since this is a volumes question, we give our answer in cubic units. Okay, but actually we do have the units. It's not units, it's meters, so we should really give this in cubic meters. Okay, and so that's the volume required, and that's the end of part A. Part B. When an object is projected from a point h meters above the origin with initial speed v meters per second at an angle of theta to the horizontal, its displacement vector, t seconds after projection, is given by that vector that they've given to us there, and we don't have to prove that. So what's the actual question? A person standing in an empty room which is 3 meters high, throws a ball at the far wall of the room. The ball leaves his hand, or the ball leaves their hand 1 meter above the floor and 10 meters from the far wall. The initial velocity of the ball is 12 meters per second at an angle of 30 degrees to the horizontal. Show that the ball will not hit the ceiling of the room, but that it will hit the far wall without hitting the floor. Okay, so this is a projectile motion question, and projectile motion often scares people, and I think the reason for that is because a lot of the time they can't visualize what's going on unless a diagram is given to them. Now here a diagram isn't given, we need to try to understand what's going on, so we're going to draw up a diagram to see exactly what's happening. So we've got some room, which is 3 meters in height, and a ball or an object, something is being projected towards the far wall. This is the far wall over here, and we're trying to hit this far wall. Now it's being projected from a height 1 meter above the origin, or 1 meter above the ground in this case. So our orange dot here is going to be the initial position of the object that's getting projected. And we want to show that with the conditions given to us, with an initial velocity of 12 at an angle of 30, our path is going to be something like this. It's not going to hit the ceiling. That's easy enough to visualize. But we want it to hit this far wall before it hits the ground. So we want it to do something like this. Or we also know that the far wall is 10 meters away from this point of projection. We want it to do something like this, where it hits the wall before it hits the ground, as opposed to maybe something like this, where it didn't hit the ceiling, but it hits the floor before it perhaps bounces and then hits the wall. So we want the blue scenario and not the green scenario, okay? All right, now, I'm going to write down the initial conditions that we've been given. Maybe I'll put them up here. V was equal to 12 meters per second. Theta was equal to 30 degrees. And what I'm going to do is I'm going to substitute these into my equation for RT, the displacement vector. Okay, so for our particular scenario, we've got R of t equal to V, which is 12, t cos theta, that's cos 30, and cos 30 is root 3 on 2, times I, plus negative 5t squared, plus 12 t sine theta, so sine 30, which is a half, plus h. Now what's h? It tells us in the question that this equation that they've given us, this displacement vector, this applies when the object is projected from a height h meters above the origin. So in this scenario, we can basically take our origin to be this point here. And so that height is 1 meter, so h is 1. So if you like, we've actually got some axes here. Here's the y-axis, and here's the x-axis. Okay, but h is 1, so it's plus 1 j. Okay, we can simplify just a little bit. This will be 6 root 3t times I, plus negative 5t squared, plus 6t plus 1 j. Okay, cool. So we've got the displacement vector for our particular scenario, and let's just remind ourselves what we're trying to do. We're trying to show that it's never going to hit the roof, and we're also trying to show that it will hit this far wall before it hits the floor. Okay, so let's start off with the fact that we want to show it doesn't hit the ceiling or the roof. How would we do that? Well, if we can just find the maximum height of our trajectory, of our particle or object, and show that that's less than 3 meters, because 3 meters is the height above the origin, well then if it's less than 3, it's never going to hit the ceiling. So we want to try to find the maximum height. So that's our sort of sub-goal at the moment. Now, how do I find a maximum height? Well, I know that at the maximum height, so if it's the case of the blue curve, like this, this is the turning point of the path. And we know at the turning point, the velocity, the y velocity, is equal to 0. So I'm going to have to work out what the velocity in the y direction is. So I have to work out what y dot is. Now we've got y equals minus 5t squared plus 6t plus 1. So y dot is going to be minus 10t plus 6. And I can say that the maximum height occurs when y dot is equal to 0. And so therefore I'm trying to solve 0 equals 10t plus 6, which would give me, let's see, 6 on 10, which is 3 on 5 seconds. Or if you like, 0.6 seconds, either is fine. So this tells me when the maximum height occurs. Now to actually work out the maximum height, I have to substitute this time into my y equation, okay? Because the y equation is telling me the y value, the height. So therefore, my maximum height is actually going to be equal to minus 5 times 3/5 squared plus 6 times 3/5 plus 1. Putting that into the calculator should give us a height of 2.8 meters, and well, that's less than 3, so I can say this is less than 3 meters, and so therefore we can make some sort of concluding statement like this. Okay, so since the maximum height is less than the height of the room, the particle is never going to hit the ceiling, okay? And so we've shown that first part that we wanted to show. Now, what was the second part again? The second part was that this particle, when it's projected, will hit the far wall before it hits the ground, okay? So how could I show that? Well, if you think about this scenario that we have in blue, if this far wall wasn't there, what would be happening? The particle would continue along like this and would eventually hit the ground somewhere over here. So what I can try to do is show that if I find my horizontal range, the horizontal range being that distance there, if I find my horizontal range and show that it's greater than 10, then that would mean that it would have to land somewhere out here, basically outside of the room, which means that it would first have to hit the wall. If I found my horizontal range and it was less than 10, so a scenario like this, that means it bounces before it hits the wall, and that's not what we want. So it's all about finding the horizontal range here, okay? So we need to essentially find when does the particle hit the floor, and then we have to substitute that time into our x equation, which is 6√3 times t. So I can start off by saying the particle lands, or particle hits the floor when y is equal to 0. And so I have to solve this equal to 0 now. So we've got minus 5t squared plus 6t plus 1 is equal to 0. This is just a quadratic, so I'm going to just hit it with the quadratic equation. I can't see a nice factorization here. So t equals. Okay, we get down to these two values of t. Now, you'll notice that the positive case would give us a positive value, but the negative case is going to give us something that's negative. And I can tell that without a calculator because 14 is greater than 9, and so the square root of 14 will be greater than the square root of 9. So this is larger than 3. I've got 3 minus something larger than 3 is negative. So I'm going to say here, therefore t is equal to only the positive case, and I justify it by saying since t has to be greater than 0. Okay, so this is how long it would take for the particle to hit the floor, okay? And remember, we're just pretending at this point in time that this wall isn't here. So this is sort of like a theoretical when it will hit the floor, okay? All right, so now I have to substitute this time into my x equation, x equals √3t, and see what I get. So at t equals 3 plus √14 on 5, x is equal to 6√3 times this value. This is a job for our calculator. We put it into the calculator and we get something along the lines of 14.01-ish. And so I can say, therefore, the range, or perhaps we should not just say range because really it's not the range, it's the theoretical range. The theoretical range theoretical slash unrestricted range, because the wall is really restricting us. So the unrestricted range equals 14.0, well, you can just say about 14, approximately 14 meters, and that's greater than 10 meters. So therefore the particle will hit the wall before hitting the floor. Okay, and that's the end of part B. Part C. The region enclosed by y equals 2 minus the absolute value of x and y equals 1 minus 8 over 4 plus x squared is shaded in the diagram. Find the exact value of the area of the shaded region. Okay, so here we've got our region, and it's comprised of the area between two curves. And these are the equations of these two curves. Okay, and when we do a region between two curves, it's calculated by the integral of the top curve. So in this case, the top curve is 2 minus absolute value of x minus the bottom curve, which is this one here. Okay, 1 minus 8 over 4 plus x squared. So my area is going to be the integral. I'm going from -2 up to 2. So from -2 to 2 of 2 minus the absolute value of x minus the second curve, 1 minus 8 on 4 plus x squared, and all of this gets integrated with respect to x. Now this is all well and good, we've set up an integral, but the problem is I don't really know how to integrate the absolute value of x, and so I have to find another way to deal with this. And there's probably a couple of ways that you could do this. I mean, I can see one ways we could have set up our area slightly differently. Maybe we worked out this area which is above the x-axis as just simply the area of a triangle, and so then we never really actually have to deal with that function. And then we've got the area of a triangle and we add on this area. Now this is below the x-axis, so we'd have to take the absolute value of the integral. But that's one way of doing it. Another way is to recognize that this has some symmetry. This is an even function. Both of these functions are even. And so this area here is exactly the same as that area there. And so what I can do is I can write this as 2 times the integral, now going from 0 to 2 instead of from -2 to 2, of 2 minus the absolute value of x. And while I'm at it, I'm going to distribute this -1 through to both of these. So I get -1 plus 8 over 4 plus x squared. Okay, but I still have an absolute value of x, but now it's a little bit nicer because since the values of x run between 0 and 2, that means they're non-negative. And if they're non-negative, well, I can use the fact that the absolute value of x is equal to x when x is non-negative, or negative x when x is negative. So since they're non-negative, I can now replace my absolute value of x simply with an x, okay? Purely from the definition of the absolute value as a piecewise function. Okay, so this becomes 2, the integral from 0 to 2, I've got a 2 minus a 1 here, 2 minus 1, which gives me 1, minus the absolute value of x, which I'm now rewriting as x, plus 8 on 4 plus x squared, dx. Beautiful, and I'm ready to go. So this is 2 times, integrating 1 gives me x, integrating x gives me x squared on 2. Then integrating this is going to be an inverse tan. So the constant of 8 on the top, I sort of pull out the front, and then I multiply by the antiderivative of 1 on 4 plus x squared. And the antiderivative of this is 1/2 tan inverse x on 2 from 0 to 2. Now we sub in everything that we can. So I get 2 minus 2 plus 8 times 1/2 is 4. 4 tan inverse of 1. Minus, now I sub in 0, I'll get a 0 minus a 0. Tan inverse of 0 is 0, so this will actually be plus 0. And what am I left with? 2 minus 2, well that's 0. 4 times tan inverse of 1. Tan inverse of 1 is pi on 4. 4 times that is pi, and so I have 2 times pi, which is 2 pi. It's an area, so it's square units. And that should be our final answer. Now for the final part, D. Part I says, the numbers a, b, and c are related by the equations a equals b minus d and c equals b plus d, where d is a constant. Show that sine a plus sine c over cos a plus cos c equals tan of b. Okay, so what we've got here is this statement that we want to prove. And since this is a proof, I have to start with one side and end with the other side. So I'm going to start with my left-hand side and try to make my way across to the right-hand side. Now we're also given that a and c are related in a certain way. They're related by those two equations. So I'm going to replace a and c with those two values or two equations and see what I can make of that. Okay, and so this is what we get. And I'm recognizing that this looks a lot like something that we find on the reference sheet, which is the sum to product formulas. Okay, so I'll put those up on the screen now. And what we're going to do is we're going to use the sum and product formulas to turn these two sums into two products. Okay, so our numerator is going to become 2 times sine of b times cos of lowercase d, and then this is divided by, our denominator becomes 2 times cos of b cos of d. Okay, and I'm going to indicate that I'm using the sum to product formula by saying using sum to products. Great, and now I can see there's some cancellations, cos d with cos d, 2 with 2. I'm left with sine of b on cos b, and of course that just leaves us with tan b, which is our right hand side, and so that's the end of that proof. Now what does part 2 say? Part 2 says, hence or otherwise solve sine of 5 theta on 7 plus sine of 6 theta on 7 divided by cos of 5 theta on 7 plus cos of 6 theta on 7. So I'm just going to really quickly write that down. Okay, so here's what we're trying to solve, and I forgot to say that we're solving it equal to root 3, and also, which is another really important part of the actual question, is that we have a restriction on our domain, thetas between 0 and 2 pi. And so I notice that this fraction here looks tremendously like this fraction up here in what we were trying to prove. Okay, and so I'm going to try to work out what b is using the fact that I know that a is going to be this and c is going to be this. Okay, so I know that a is 5 theta on 7, which means that b minus d is 5 theta on 7, and c is 6 theta on 7, which means that b plus d is 6 theta on 7. Now if I'm trying to work out what b is, because I want to rewrite this whole thing here as tan b, I'm going to, I've got two equations simultaneously, I'm going to solve them simultaneously, and here I'm just going to add them up. So adding these two up would eliminate the variable d. I get 2b equals 11 theta on 7, and so b equals, let's see, that's 11 theta on 14. Okay, so I've got b. Now I can essentially, from this line here, now start solving this, because I get that tan of 11 theta on 14 is equal to root 3. And this is quite solvable because what do we have? We have tan, one trig function, equal to one number. Very easy to solve. This now becomes a 2-unit trig equation. So we're doing this in the first quadrant and the third quadrant, because tan is positive in the first and the third. So tan of what gives me root 3? That would be tan 60 or pi on 3. And so in the third quadrant, that would be pi plus, which gives me 4 pi on 3. To get theta by itself, I multiply by 14 on 11, and so I get 14 on 33 pi, or I get 4 times 14 is 56 on 33 pi. And those are our two values. And yes, they do fit between 0 and 2 pi, which is good. Okay, and so that's the end of part D and the end of question 13.